So the first step we do is take your, this is the first step, upside down because we're doing things in reverse order. So, first thing we do is we take a target cube, and we're basically going to have a lot of really long guys. We'll force you to, in a row, and you see that in these kinds of puzzles, you tend to have straights of length 3, like this. These are 3 3s in a row, and we're making a 3 by 3 by 3 cube, so that sort of has to live in, well, do weird things. But it's relatively restricted. You can do something like this, but then these must be the edges of the cube in that case. So we have a bunch of those, and lots of care, and we end up reducing the cube to a box, meaning we cover all of the cube, we're forced to cover all of the cube and leave exactly a box behind. Sort of like what we did when we were doing squares into square. We put a bunch of big boxes that were relatively constrained, and it just left an empty space, which is a box. Here it's actually forced exactly. Then once we have a box, so the box will be this wide, and it will go over this way, but it won't have this sort of fine feature stuff. This will just all be filled in as a box. Then this step that's drawn is to carve out this puppet spoke shape. And that's based on a structure like this, where you have a huge thing, and then a relatively short thing of length about 8 t, and then we go down, and then immediately back up, and then over and down, up, and so on. And that roughly carves out this structure. You have to be careful that this is actually unique. But we have some, this is why we only want the height of this box to be 8. Then you can't go out of plane very much. And this, while this is short, it's longer than 8. It's bigger than 1. So you can't have this spoke go up. So it does have to live in a plane. Right? This is much smaller than huge, so you can't hold it some other way. So that's pretty much forced, and then we have to get rid of the other 7 planes, which we do with really long guys. So, unfortunately, we don't have all of that drawn, so it's especially hard to see. But this is a rough idea of how you start with a box, and you do these sort of infrastructure gadgets to just carve out the shape you want, and then then you go into the interesting part of the chain. This is all at the beginning of the chain, and it's forced to do all this. And then we start, say, here, with some zigzag, and then an AI gadget, and so on. Easy, right? So, you do see here, I would say, a very algorithmic approach. I mean, this idea of showing that zigzags are universal, they can make any shape. This is something we do in computational geometry all the time. We prove that this folding structures fold into whatever we want. So we hadn't proved this one before, but we were armed with a lot of algorithmic tools to do this, and that led us to this reduction. So lower bounds, in our case, is really all about designing the right algorithms to give you powerful gadgets. That's why this is called algorithmic lower bounds. Other questions about snake cubes? I think we want it to be a multiple of 4 so that it's compatible with the grid. Yeah, that seems clean. That way we can predict if we leave on this 4x4x4 thing, we know which one will come back on. It could be in a half grid position. Any questions? I mean, you might be able to make that work, but the advantage of hardness proof is because it's not a real algorithm. I mean, it's not an algorithm you want to run. The point is to show the problem is hard. You can be inefficient in lots of places. As long as it's still polynomial, it doesn't really matter, except for drawing the pictures. That's one place where it matters. All right, that's snake cubes. Going to go on to another packing problem. So we've seen rectangles into squares, squares into squares. How about circles into squares? So this is a real life puzzle where you have, I think they're water jet cut or laser cut metal discs, and you have to fit them into this box. So these are real life puzzles. That's one motivation. There's a stronger motivation for studying this problem. This related to computational origami. There's this method called the tree method of origami design. If you're interested in it, you can 66649 or read Robert Lang's book, Origami Design Secrets. And basically it lets you fold things like this. That's at a high level. And a key component of it is to pack discs into the square. The square is your piece of paper. The discs correspond to sort of the limbs of your creature. And you can't use the same piece of paper to represent this limb and this limb, so the discs have to be disjoint. It's all about packing those discs into the square. And yeah, so that's at a high level why I care about disc packing. And people have thought about disc packing a lot, but surprisingly it hadn't been proved hard until 4 years ago. So, this proof is also complicated. So, and it involves a lot of geometry and trigonometry and some calculus and fun stuff. So I'm going to give you a sketch of it. It should be believable that this works, but the details, again, are messy. For starters, let's say that we're packing disks into an equilateral triangle. This is much easier to work with. I'll go to a square in a second. So if I have this equilateral triangle, what I'm going to do is first I'm going to give you a bunch of disks that are forced to pack in this nice triangular grid arrangement, leaving these dark holes. And I'm going to give you more disks, and so the more disks have to go into those holes. These are actually kissing disks. They're touching, so you can only put, every disk you put from now on will be in one of these holes. And I'm just going to do this big enough so that I have at least n over 3 holes. Each hole is going to represent a bin that I'm trying to put a triple of numbers into. And then here is the construction for, I guess this would be a 3-partition gadget. We want to get this, so I type of the AI plus AJ plus AK is less than or equal to T. And so these are the 3 disks representing AI, AJ, and AK. And there's an extra disk in the center. And what's drawn here is everything is maybe tight, almost as touching. But we're going to shrink these disks a little bit, or rather, I'm going to shrink, yeah, I guess I'll shrink, that's right. I'm going to shrink this disk a little bit, and I'm going to make these ones a little bit bigger, according to the AI values. So this one will be proportional to AK larger than the disk that would perfectly fit here, if this one was maximally sized. And so that's going to force this guy to move away. Well, it's a little bit shrunk, so maybe he doesn't have to move away. But this center disk, when it's shrunk down, it has a little bit of flexibility. It could move more this way. If this disk is smaller, it will move more this way. It can move more this way, more this way. And in general, you show that so these guys are sort of placing demands by being a little bit bigger. They need to push out. And this one is a little bit smaller, and its size is just a function of T. And so it's going to move around, and the claim is it has a valid position if and only if AI plus AJ plus AK plus T. I have written down a little bit of the details.
戦後70年、喜びも悲しみも歌とともに 歌は時代を超える、そして私たちの心に宿る、そんな思いを強くしたひとときでした。
そして思い出の名曲の数々、皆さん素晴らしい歌声でしたよね。北島さん、
みんなね力入ってる、本当すっごい今日迫力があって、これお客様が最高なんですよ今日は。本当にありがとうございます。なんか変な汚い司会でさ、ごめんなさい。
ちょっとお司会ありがとうございました。
どうもありがとうございます。
さあそれでは生放送でお送りしてまいりました第47回思い出のメロディー、締めくくり総合司会の北島三郎さん、ご紹介をお願いいたします。
それでは皆さんとご一緒に青い山脈だ行こう。